that did have fragrance to it, right? So trans, anethol, and estragol, those are things from fennel. Not not the fennel that you're hopefully used to by now. It's not a functional group, right?
Okay,
FENYL, not PH. And anise, so that licorice-like flavor or scent. Myristicin, I believe, is nutmeg. Eugenol is clove, and isoeugenol is not from cloves. I don't remember where that's from. It's slightly different in that here we have an isolated pi bond, right? And over here it's a conjugated pi bond. But these are the things that gave aromatics their name. Okay, so initially, chemists are like, oh, these compounds have an aroma to them. But please keep in mind that not all aromatic compounds will have a smell to them. Okay, that is a relic of the ones that did when they were first isolated these things.
Can I ask, in 103 you said you identified like the essential oil for the smell of the trees, the like vanilla type smell. Do you remember which compound that was?
Benzaldehyde.
Benzaldehyde? Okay, cool.
Yeah. Yep.
Are those the butterscotch smell from Jefferson Pine?
Yeah.
Okay.
Yeah, or butterscotch or vanilla. Some people have different descriptions of it, but yeah. So sugar pines, really, it's probably the same thing in Jefferson Pines as well. But yeah, it's benzaldehyde. And actually, I think it's on this side. It's right here.
Oh, that's
Benzaldehyde.
cool.
Which we'll get into in just a minute. So, aromatic compounds are highly prevalent in pharmaceutical drugs. And in fact, the majority of, if not all, pharmaceutical drugs will have typically some aromatic compound in them. And partly because aromatic compounds, as we'll talk about, are really stable. All right? The most popular aromatic compound that you guys are familiar with, I'm sure, is, and forgive me, it's been almost a year since I've had to draw a hexagon, so.
Oh yeah. Still learning myself.
So you get, I mean, that's the one thing about OChem, you get good at drawing hexagons, but like with anything, you get out of practice and, you guys remember what this is?
Benzene ring?
Benzene. Yeah. It's really stable. I'm sure Sean talked about it, right? It has resonance, right? Maybe did he describe it as the unicorn dancing around in the stable? The happy unicorns, right?
Like a donut, yeah.
Yep, circling around. So sometimes they'll write it like this,
Oh yeah.
you know, to show that these bonds are moving around. Actually, this is not, neither one of these are truly correct because it's kind of in between, right? So rather than it being like one pi bond each, it's like 1.5 pi bonds because they're constantly resonating, right? So at any given moment, you can have these different structures, but it's highly stable. And aromatic compounds in general are going to be stable. You want your drugs to be stable, right? That's going to increase their shelf life. You don't want them to be so stable that they can't be metabolized, though, right? Drugs are only good if they're there for a certain period of time. my kids are still incapable of understanding why they can't eat a bunch of Tylenol all the time. Because it tastes, they get the chewable Tylenol, you know, or the liquid, it tastes good. I'm sick, I need medicine. First of all, you're not sick. My arm hurts, you know. Well, I don't know if maybe your arm does hurt, but you just had Tylenol. Well, more is gonna make you feel better, right? Well, they don't realize that at some point a medicine can be toxic, right? So we gotta be able to break these things down. And keep in mind that a lot of our macromolecules, our organic molecules, have aromatic rings in them. Okay? So the nucleotides, the amino acids, even some of the lipids and carbohydrates have these aromatic compounds. And so in order for medications to bind properly, right, they have to have similar docking pockets, right, that we call enzyme and substrate. And so in order for that to facilitate, we have to have similarities and commonalities, right? So we see aromatics in pharmaceuticals and in essential oils, but we also see them in things like us, which is why it's called organic chemistry, right? Because these are the molecules that are often associated with life. Not all, of course, but a lot. All right, you know, we will have on the midterm probably some question where you have to do nomenclature. You've been doing nomenclature the last couple of quarters. It's not particularly going away. You take a benzene ring, you add a substituent to it, and you name it accordingly, right? So IUPAC would call this chlorobenzene, nitrobenzene, ethylbenzene, so on and so forth. However, there are some pre-IUPAC names that are still allowed by IUPAC, right? And I'm sure Sean's told you IUPAC, you know, can be a little funky. There are, you know, it's great. It's actually essential. We have to have some kind of standardization, but IUPAC allows certain artifact nomenclature in there. So we will refer to things like this. So you could call, we could call toluene, we could call that methylbenzene, right? But more likely than not, you'll see it referred to as toluene, right? We could call, if we had a methyl here and a methyl there, that becomes xylene. And so, right, 1-methyl, toluene, 2-methyl, xylene, and these methyls can be at different places. Anybody know if they're on opposite sides, what we would say that is? It's one of those, but not ortho, it's P, para. So think, you know, opposite sides. We could have something like this. That would be, guesses? Not para. Oh, see, that's why we're going to review a little bit, right?
I remember that.
So meta. So meta actually means once removed. It's often used nowadays, if we have meta majors, it's used to be like, it's considered like all encompassing of a certain thing, right? Or a meta-analysis is like diving into the literature on a certain topic and summarizing it. But really what meta means from a Latin standpoint, or Greek, which one it is, but it means once removed. So here's one group, removed, once removed from that. So then ortho-lex would be when they're right next to each other.
Okay.
And this would be O-xylene. And what helps me think about this is going back to those worms I was talking about that I studied. We have 25,000-ish genes in our genome, human genome. These little tiny worms that are just barely visible. I mean, they're almost microscopic. They don't have eyes. They don't have a tongue. They have a very rudimentary intestine made of 20 cells. Very simple. They're clear, they're transparent, so you can look at all of their cells under a microscope. They have 20,000 genes. So even though they're tiny and they're what we would say very simplistic, they only have maybe 5,000 less genes than we do. And of those 20,000 genes, 40% of them have what are called, you don't even know this, but have orthologs. Meaning, not orthogs, it means that their genes are orthologous to human genes, meaning their gene A is basically our gene A. Okay? So ortho means next to, proximal. Okay? Orthopedics, right? Ortho is the proximity of your bones, how they articulate. Particularly be familiar with toluene and phenol, because that's going to pop up a lot when we talk about certain compounds. Andesol and aniline, a little bit. We'll talk about those. I mean, the nice thing is phenols and toluenes are pretty easy to recognize. If it's a benzene with a methyl, it's a toluene. If it's a benzene with a hydroxyl group, it's phenol. Benzoic acid, that should be pretty straightforward because you guys know what carboxylic acid is, right? It's that group, right? So benzoic acid, that's often used in like acne creams and stuff like that. It's an antimicrobial agent. Benzaldehyde, that's what's in vanilla extract.
Okay.
Interestingly, you can buy vanilla flavoring. Right? If you go to the store and you go to the Spice Center, the spice aisle, you can get vanilla extract or you can get vanilla flavoring, and they're not the same. They're not the same price. Right? If you look, vanilla flavoring should be a lot cheaper. Because vanilla flavoring, I should say, is synthesized.
Okay.
It's just benzaldehyde, it's this molecule. And if you look at it, it's clear. Vanilla extract is taking a bunch of vanilla beans, grinding them up, right? Pressing them, maybe doing some distillation. And so the input for that is much more costly. And if you look at it, it's dark.
Okay.
And it's not just benzaldehyde, it's got whatever other chemicals came in the process, right? So just, next time you're at the grocery store, check that out.
Yeah.
They're different. Vanilla flavoring is just this molecule right here. Acetophenone, styrene. Styrene is actually a pretty common compound as well. If you take a styrene and you attach it to another styrene, and attach that to another styrene, and you get a long chain of styrenes, or you get a polymer of styrenes, we call it polystyrene. I know what polystyrene is. Styrofoam. So styrofoam is just a bunch of these linked together.
And that's why it doesn't break down, because the benzene ring is really stable.
It's really stable, and the bond between the bond that attaches here, we break this pi bond here, and we attach it via that. So it's a link. It's a link of this region here. I guess did Kathy write on this?
I don't remember.
No.
Yeah.
I'm just gonna try.
Okay.
Yeah, I think that'll work. Teach them for giving me numbers to work with.
Schedule that on your week off. Yeah.
Not like he's like, oh, you didn't come to the training. Well, it was during spring break.
Yeah.
That was out of town. In Europe and stuff, it's called polystyrene. Styrofoam is a brand name, like Kleenex is tissue paper, but Kleenex is a particular brand of it. Styrofoam is a particular brand, DuPont or something, probably DuPont, something like that, of a bunch of styrene molecules stuck together. All right, so how do we do this? We can use IUPAC, or we can use the more traditional naming. So for instance, if we have, let's look at this anisole, right? So anisole, if you look back on that previous page, right, is this molecule here. And then what would we call this functional group here? Ether. Ether, right?
Yeah.
An oxygen sandwiched between two carbons. Ester's close, right? You got that double bond with an oxygen. So that's the parent, right? Anisole. Okay, we put a nitrogen group on there. We call it nitroanisole. And if we put it here, it's ortho. If we put it here, it's meta. If we put it directly across, it's para. Same thing here. Toluene is the benzene with a methyl group. We're adding a bromo. Toluene. And they're meta in relationship. Para and so forth. Now, the other way to do it would be to use numbers, right? So instead of using the ortho meta para, we would have this be number 1, because this is part of that parent name. So it gets the first designation, right? So then that means we're not going to go 1, 2, 3, 4, 5, 6, right? Because as you have all learned, you want to keep the numbers as low as possible. Now, Sean was not a big stickler on alphabetizing, right?
No, not really. Yeah.
Okay. I'm not either. I mean, I was. I used to be.
Yeah.
But then I realized that Sean wasn't, and so I'm like, okay, I would be either. But it's important to know about alphabetizing. So like MCAT, I don't know if you've taken the MCAT yet.
Yeah.
You have? Okay. Well, then never mind. I don't know. Maybe they did have alphabetizing, but like, if you go on in organic chemistry at some point, there might be issues with alphabetizing. So if you were to take the MCAT,
It was good to know, because like in the paragraphs, if they're like naming different types of compounds and
stuff, it was, that
Yeah.
was like the way that it was
Okay.
being written out.
Yeah.
So it was like good to know.
And
about.
some people, people would mark it wrong if it wasn't alphabetized. But I think he's on to something that, as long as you can draw the molecule from the name, who cares, right? As long
When
as
it was
it's
like
not
die or
ambiguous.
try, he said it was kind of like conflicting whether that the prefix would like
Well-
consider the alphabet.
It only does in certain circumstances.
Oh, okay. Yeah.
So that's why it gets confusing, because sometimes di and tri and tetra are part of the alphabetization. And sometimes they aren't. Or sometimes di, tri, and tetra, etc. are, but something like iso isn't. So that's where IUPAC gets a little finicky. It's a little touchy, and it's a little like, oh, well, there's this exception. It's kind of like, anybody played Settlers of Catan?
A while ago, yeah.
If you're learning the game Settlers of Catan for the first time, they can't tell you all the rules to the game
Yeah.
at the beginning. Just take too long. So they give you the gist, and then as you're playing, you're like, oh, well, actually you can't do that. Well, why didn't you tell me that at the beginning? Well, and then you play somewhere. Oh, well, you can't actually. No, you can do this only in this circumstance for the wheat, right? So that's kind of like when I think about UPAC, I kind of think of Settlers of Catan in that way, teaching someone a noob about it. So that's why I'm fine too with not being too much of a stickler on that. And then, same thing, meta or 3, para or 4. If we move this here, right, 1, 2, 3, 4, if we move it here, it wouldn't be 5, right? We would just reverse our counting, 1, 2, 3. So I was mentioning how stable these aromatics are, and if you were to take this this compound here, it's not aromatic. Okay, and again, we haven't classified what aromatic compounds are yet, but what would this be? Anybody know what this is?
Hexene?
Yeah.
Cyclohexene, yeah.
Hexene. If we were to take cyclohexene and hydrogenate it, the energy, potential energy, drops, okay, into just cyclohexane. And that drop is 120 kilojoules per mole. Right? So we're releasing that amount of energy. It's becoming more stable, right? So by inference, we would assume, okay, well, to break that pi bond and put on those hydrogens, we get 120 kilojoules per mole of energy released. If we had 2 pi bonds, it should be about double that. And in fact, it's fairly close. It's a little less, right? It's not like 240 would be exactly double, but it's a little less than that because there's resonance here. And resonance equals increased stability. Okay, so it's roughly that, but because there's some resonance, it brings it down just a little bit. Well, okay, let's extrapolate that further. If we have 3 pi bonds, it should be 120 times 3, because each pi bond is 120 kilojoules per mole of energy released. 360. Turns out that's not the case. Right? When they measured this, they realized that what they expected was higher. The benzene here actually only releases a negative 208 kilojoules per mole. So that's 152 kilojoules per mole less, more stable, in other words, right? Because we're plotting energy this way. As we get rid of these pi bonds, the energy goes down. Okay. So the amount of stability it has is more than this order of magnitude here. Or not order of magnitude, but this magnitude, I should say. And that was interesting. Huh. Why is that? Well, it's because benzene is super stable. Because it has resonance, and it has resonance in a balanced way, right? I mean, there's resonance here, right? There's resonance there. But at any given resonance here, you have essentially the same distribution, right? This is not evenly distributed throughout that ring. Right? So we write it like this, and we talk about the happy, magical unicorns trotting around in the stable. In the stable, because they're stable, or the corral. You know? So the point is that aromatics are more stable than what we would predict. This is not an aromatic compound. Okay. This is not an aromatic compound. This is an aromatic compound. You guys learned about molecular orbital theory. Yeah, was that back in OChem 1? Or was that last quarter?
We were talking about it last quarter, the homo limo.
So why is benzene so stable? There are 6 isolated p orbitals, right? And when we plot all these out, we have energy increasing, right? So this stuff, less energy, more favorable, more stable, right? If something's super high in energy, it's not going to be stable because it's requiring a lot of energy to maintain that. And if it can just break apart, it will. So red, blue, you guys understand. Did he use, does this look familiar? Not this exact figure maybe, but does this look familiar?
The anti-bonding orbital.
The anti-bonding?
Yeah.
Okay.
We talked about
So what we're looking at is the p orbital overlap here. Okay. And these are nodes. Talk about nodes. So the nodes are going to be where there's some interference. Yeah. We have these 6 electrons, and it turns out that we can fill these 6 electrons in these 3 bonding phenotypes. And they're all bonding, not anti-bonding. This obviously is the most favorable because there's no node and it's completely overlapping. But these are the next best thing because there's only one node here, right? And so what makes benzene so stable is that it doesn't have to go in. I mean, it could, right? Here are a couple nodes. Here, the same number of nodes, but there's less overlap, right? Here's even more nodes. The more nodes, the less stable, but they don't have, it doesn't have to jump up into this configuration because it can satisfy those pi bonds in all of these bonding molecular orbitals.
And those kind of represent like all the p orbitals from each carbon coming together, so the molecular orbital.
Yep.
And what causes the nodes, like how much energy is being put into it from the environment?
What causes the node is the relationship. Well, yes, I mean, it's always, I mean, yes, that's the answer, energy, right? In chemistry, like I say, it's always The answer is always electronegativity, right? But yes, it's always energy too. The nodes are whether or not you have remember con rotary, syn rotary, right? These opposing orbitals, how they are arranged together.
Oh, okay.
That's what affects HOMO, LUMO. You guys remember that?
Yeah.
Okay. So light, whether that light or heat is involved, but the orientation of these things, when it's wrapping around into that ring, if these are aligned or if they're not aligned.
Oh, so it comes before it's a ring. The orientation determines that, or
Yeah.
oh, okay.
The orientation of these, and then as that forms the ring, where those orbitals are in their respective position will either create a node or not.
Okay.
And a node is just, yes, energy. It's the vibrational frequency that's happening as a result of the interference or lack thereof. Right? So, well, we're out of time. So, but on Thursday, we can do I can try and throw in a slide or something that shows that. We can review that.
Yeah.
So, this is kind of where I guess we'll leave off.